Do you want me to leave this presentation up? You can use the keys here, or you can use the mouse, however you normally would advance your slides.
You could advance the slides backwards and forwards.
Okay. Or you can use this. Okay.
Okay. This session is again very different from some of the sessions we've had in previous AMS-WMA meetings. It's called New Unconventional Concepts and Legal Ramifications. Ugly word, legal ramifications. But and actually, we're going to have a paper later on in the week dealing with legal issues and weather modification from a person that hasn't attended these conferences before. So we look forward to that. A professor coming from the University of New Mexico. But first off, in this session, session 2, Atmospheric Heating is a Research Tool by Lyle N. Jenkins from Eastland Scientific Enterprises Corporation, Houston, Texas, and his co-author, B.J. Eastland. Mr. Jenkins.
All right, I've got to start off with a couple of stories. The one thing, my co-author has abandoned me because he died in December, and I was able to cobble together enough of his part of the paper to define or at least get the paper out. And I'm a little soft on some of the concepts on the plasma shield and that, because my background is in engineering, aerospace engineering. I worked for NASA for 38 years and had retired recently. So the Jenkins Enterprises is kind of a small organization to write off the expenses on this trip. But he mentioned one of the things, my daughter graduated from the University of Texas and in the accounting area and came home and rebelled. She said she wanted to become a lawyer, and so for an engineer, that things put things in perspective. But certainly the legal ramifications are an aspect that we need to understand before we start using a lot of these techniques. Now, the thing I want to bring in is use microwave beam as a tool to research and understand the weather. So I'll try to go through this and be able to define the particular aspects of the early stages, but my ultimate goal is to provide a basis for space-based solar power as a clean, renewable energy source. And that concept I'll show in one of the slides here. The climate change, I think, is a reality, and space-based solar power, though, can provide a clean, renewable energy source. But there's certainly a lot of uncertainty in the development of space-based solar power, which we took a particular aspect of that and used space-based solar power to provide a capability to heat the cold rain downdraft in a thunderstorm to prevent tornadoes, and we'll go into that concept. But the potential benefits, we think, will support the demonstration of the elements of space-based solar power. Certainly, there's one aspect here that we want to, and I think these are guidelines that the National Academy of Sciences outlined, but certainly base it on theoretical modeling and simulations. define the potential for instability and chaos, do some small-scale mitigation experiments, and then define the requirements for the design, development, cost analysis of deployment systems. But we want to study related natural events, the potential side effects. So the particular research concept that is the creation of a plasma pattern in the high altitude, and Ben Eastman had come up with an idea that he could leverage the effect of cosmic rays to reduce the energy requirements for the plasma pattern. So if we can establish the plasma pattern, then there are certainly some ways to be able to evaluate and use that to define certain weather phenomena and provide a basis for the computer analysis of thunderstorms and weather systems. And Ben was involved in this high-frequency auroral antenna research project, which was somewhat infamous. It's the HAARP project on the North Slope of Alaska, and I'll describe that a little later. But here's the concept that Ben defined, that we could have a pattern-forming beam that is associated with a particular heater, and the idea was to create a plasma pattern in the upper atmosphere. And again, Ben we didn't get a chance to discuss why these cosmic particles can reduce the energy requirements for producing the plasma pattern. But his concept was to form a pattern, wait for the particle to trigger the plasma, and then apply more energy to create the plasma pattern. There's a little background on these ionospheric mirrors, and again, I'm very soft on understanding a lot of this sort of thing, and so I'll kind of slide past this, but the bottom line was that they haven't been produced because of the power requirements, and his idea of using the initiation of cosmic rays to trigger the pattern may indeed produce some results. So kind of an overview of the weather modification concepts. Certainly, and my frustration in attending the meteorology conferences has been that you mentioned weather modification, it's always related to cloud seeding. But there are some other concepts using oil slicks to moderate hurricanes, atmospheric heating to steer a hurricane, and using the selective heating to disrupt the convective shears that produce tornadoes. So our particular concept on the tornado prevention or disruption process is the concept called a thunderstorm solar power satellite. The solar power satellite concept was developed by Peter Glazier back in the 60s, and the idea was to lay an array of solar cells out in geosynchronous orbit convert that energy into microwave energy, beam it down to the surface of the Earth, convert it back into electricity, and pump it into the commercial power grid. And the thunderstorm solar power satellite then would be a small version of that, and the main output would be a concentrated microwave beam that would go into, well, we try to identify a key volume in a storm and direct intense energy into that area, and by warming the cold rain and the downdrafts, that we would disrupt the convective shear process in the thunderstorm. And one of the issues would be the beam absorption by the raindrops. We would hope would absorb most of the intense microwave energy before you cook the people in the trailer park that you just saved from the tornado. So there's pluses and minuses involved in the particular aspect there. So we definitely need interactive feedback on the absorption and the effect of the beam in order to direct it into a particular area. And here's an overview that the new scientists put together. You have the solar power satellite. Let's see, where's that pointer that... Okay. Oh, okay, sure. Yeah. Okay, so we got our solar power satellite, and we need a computer simulation to tell us where in orbit. We'd like to not go all the way out to geosynchronous orbit and maybe have the satellite in a sun-synchronous orbit, so that we're over Tornado Alley at the appropriate time in the afternoon, that the thunderstorms are likely to produce tornadoes. But the idea was to then, the idea was to generate a microwave beam at a particular frequency that is tuned to the cold raindrop size, do some selective heating to affect the downdraft, and that in turn would disrupt any convective shears that are creating the tornadoes or concentrating the energy in the tornadoes. So tornadogenesis is not well understood. We think that they form only in about 20% of the thunderstorms. That we need to identify, and that whether people have improved their identification of precursors. Certainly the warning times have increased, but there are a lot of complex interactions here that need to be defined, to put into the computer program to tell us where in the thunderstorm to focus the particular energy, how much energy we would need, and where in the storm, and the duration of the energy input. But it depends on the definition of the fine structure of a supercell thunderstorm, and we'd only looked at supercell thunderstorms as being a potential for interaction here. But we did get the CAPS at University of Oklahoma to put selective heating into their computer program simulation of the thunderstorm, and determine what the microwave heating would be. And in this particular simulation, we put a tenth of the standard reference solar power satellite, which the reference satellite was at 5 gigawatts, so Ben had them put in half a gigawatt into the cold rain downdraft, and it just totally wiped it out. And so we've since then had to point to that, saying we can interact with the thunderstorm, but we need to refine that interaction. And at that stage, the simulation didn't show tornadogenesis. Since then, Ming Shui has been able to improve the HAARP simulation to show the formation of tornadoes. But we haven't had access to that to interact to see what sort of requirements would be needed to prevent the tornadoes from forming in the thunderstorm. But certainly in the HAARP simulation, we need a definition of the initial conditions, need atmospheric temperature, pressure, intensity, and we think that the plasma shield could provide some of these measurements. And more recently, we saw a thing where GPS signal analysis may also provide some information on the atmospheric parameters. But we think we need close to real-time input to the simulation to interact. If we're going to try to interact with the thunderstorm, we need to have a good definition of that particular thunderstorm. So this is an output that Ming Shui had from his HAARP's computer simulation demonstrating the tornado formation, and I'm still not convinced that we really have a grasp on how the tornadoes form in the. But the issue here has been that he runs his simulation on a supercomputer back in Pittsburgh, and he's not even on site there at University of Oklahoma. So getting the computer simulation of the tornado formation process needs to be simplified. So we've looked at some demonstration concepts, and one of the things, the critical things, is the transmission of microwave energy through the atmosphere, and we've looked at some ideas of using the International Space Station as a tool to define some of these early research issues. So we would put a rectenna on the space station and have a big antenna, phased array antenna on the surface of the Earth, and beam it up and collect the energy and determine the transmission effects, the losses, and that sort of thing. And then we would hope to put an antenna on the space station, and then do the opposite, beam it down to a rectenna on the surface of the Earth. But this is an early concept of a solar power satellite, and the idea here was collect the energy as an array of solar cells, pump it into a phased array antenna, convert it into microwave energy, and beam it down to the surface of the Earth, and then convert it back into electricity. So more recently, there was a workshop at Breckenridge on space-based solar power, specifically for military logistics, where the idea was to replace hauling fossil fuels into the military in a particular tactical situation, that we could then provide the overview effect from a solar power satellite to provide additional energy into the system. And they came out with some specific goals in the workshop report, and that report, if you look up space-based solar power, it came out about last October. Anyway, national energy independence, to assist allies in their energy independence, provide economic benefits for energy export, and provide environmental benefits from reduced carbon emissions, and we think that it would provide a strategic goal for the evolutionary route to a commercial solar power satellite system that provides a measured amount of energy. So a summary, our initial indications, simulations show that we can affect a thunderstorm. We need to refine those simulations and our understanding of tornadogenesis. We must avoid adverse effects and provide them with enough understanding to preclude legal action. And this plasma heating layer may provide us an interactive resource tool that demonstrates a lot of aspects. And the space-based solar power studies will support the technical feasibility of the solar power satellite system. So space-based solar power, the objective is to collect solar energy in space for use on Earth, convert that energy into a microwave beam for transmission to Earth. And the thing that convinced me that this might work was JPL on their Goldstone antenna had set up a demonstration back in the 70s, and they beamed microwave energy across a canyon, lit up a battery of football field lights, and they did it at an efficiency for that particular length of 83%. So energy into the antenna and output to the football field lights was 83%. Now, that you sum up all the various energies, the efficiencies, and that there have been a lot of changes in solar cell efficiency and that, and it was studied intensely by NASA back in the 90s, a fresh look at space-based solar power. And when the Air Force decided to take a look at this, they drew on a lot of the resources that had been developed there. So let's see. Okay. So we think that there are certain aspects of this, and unfortunately I haven't been able to find a sponsor or tap into the right combination of things to get some funding for this research. But certainly space-based solar power has a potential to provide as clean, renewable energy from space. Okay. That's
Okay. Let's thank our speaker. Fascinating paper. Question. Yeah. More comments, but put my finger on it. One thing I get to individually, like one thing I do want to take a number. One thing I do want to comment on is that I gave a lecture in my class a couple of weeks ago on tornadogenesis.
yeah.
In that, by telling my students this would be the most controversial topic I'll give you all semester. And there's another study out here now, for example, that has shown that the cold pools are moderated out of cold.
Yeah, yeah.
It increases the likelihood of tornadogenesis. So anything you do that might decrease or make cold pools less cold is likely to increase the probability of tornadogenesis. Page Wade does some simulations suggesting that. They never got through the review cycle in 2 different journals. And we've done some simulations for the aerosol effect in diesel. Moderate the intensity of the cold pool, so the energy is likely to do that. Your likelihood is greater, it's going to increase the likelihood of tornadogenesis.
That's certainly something to be researched before we, and it depends on the computer analysis and us being able to determine the effects of how much energy and where in the system that we would put this particular energy. And it may, you're right, it may very well be that it's not the right approach to prevent tornadoes from forming in the thunderstorms.
Seems like we might have some substantial losses in directing microwave energy into a certain portion of the cloud. So how much loss would you get if it had to go to a kilometer cloud before it got to the area we're trying to?
Well, it again depends on the frequency and the interaction that you want to, the particular raindrop size that you want to interact with in the thunderstorm. And that, again, is something that needs to be analyzed. But typically, the microwaves will penetrate certain cloud cover. That's why laser transfer from solar power satellites and that is not particularly practical because of the reflective problem. But certainly the microwave energy can, at certain frequencies, penetrate.
I'll just mention that you might want to be at the panel tomorrow night because most of the proposals for modifying hurricanes have to do with altering the heating rate, location, and heating rate in the cloud structures of hurricanes. So that if it can be shown that the microwave energy can do that in a localized area, I think that's something else to think about. So we might want to add this to the next.
Well, certainly, Dr. Ross Hoffman had got funded by the NASA Institute for Advanced Concepts to take a look at steering hurricanes, and I don't know whether he has any input into.
He isn't here, but I think we did invite him, but no, he won't be able to come.
Well, I'll go ahead and try to. I've got on my microchip the output of his study, and we'll go ahead and provide that aspect tomorrow night at the panel. And
Other questions? One more, yeah.
Yes, yeah. That's the advantage of a phased array antenna is you can very quickly steer it and direct the beam, but you can also, if you're in trouble, you can diffuse it and distribute the energy very quickly.
I'm only thinking about the timing for modifying that problem of rainfall that you're talking about.
Don't know. Again, it relates to Bill's comment about the heating. We haven't been able to, even Ming Shui and Kevin Brodemeyer, we've been talking to them about interacting with the computer simulation, but they haven't given us an opening yet on that.
How big of a beam are you going to be directing when it gets down to the big river?
Well, the initial simulations were about a 50-meter diameter beam, and forget the intensity numbers that we were looking at. But it was a very intense beam, and one of the concerns was absorbing that energy in the cold rain before it got to the surface of the Earth to cause some issues there. Now, with the solar power satellites, you keep that beam energy distributed over a very large area, so it's like being close to a microwave antenna that typically you don't have significant effects about that. But so you want to keep that beam intensity down, and that's another issue about using laser as the energy transfer technique, is that you want to not have to worry about airplanes flying into it and that sort of thing, that aspect of it.
All right, let's move on to our next paper. Philip Chivio from Atmore Ocean Incorporated, Santa Fe, New Mexico, and his collaborator Isaac Geddes